Good afternoon, everybody. We'll be getting started in just a couple minutes. Thank you for joining us this afternoon. All right, we're going to go ahead and get started. My name is Sean Maurer. I'm joined today by my colleague Ryan Siegel. We'll be going over some key items for commercial building plan review in the 2018 IECC. Today's presentation is being recorded and will be available along with the slide deck at CDAC's website. We are also offering continuing education credits for IECC and AIA. Once you complete this online workshop, we will submit a completion certificate to you by email. You can reply back to that certificate with your AIA member number, and we will be sure to get those credits turned in for you. Excuse me. Today, what we're going to be covering, the quick learning objectives, understanding the Energy Code Plan Review practices for commercial buildings, learning best practices for documentation of commercial energy code compliance, and identifying commercial energy code plan review requirements. The Smart Energy Design Assistance Center is an applied research program at the University of Illinois. Our mission is to reduce the energy footprint of Illinois and beyond. This energy code training program is one of those programs that supports that mission. We are sponsored by the Illinois State Energy Office of the Illinois EPA. I'd like to thank them for helping us bring these presentations to you. CDAC provides technical support for code officials, architects, engineers, contractors, and building owners, and there are various ways to contact us. Probably the best method is to email us at energycode@illinois.edu. That gives us time to review your question, consult with our other team members, and get you the best possible answer. We do ask when you submit a question to us that you specify whether it's a commercial or a residential project so that we know the correct part of the code to refer to. We do also have a 1-800 number listed there on the screen if you need a quick answer to a question. And we also have a multitude of resources available online. It should be Smart Energy at Illinois, smartenergy.illinois.edu /energy-code. If you do use this link, it will forward to our current website. But we have access to links directly to the IECC Energy Code booklets, ResCheck, ComCheck links, the Illinois amendments, and so on and so forth. We also have links to all our past workshops and past webinars, and we have self-paced online courses for Energy Code that are geared towards entry level, so homeowners, people just getting started in the Energy Code, but can be a good refresher for people that have been working in the Energy Code for a while. Again, those are self-paced webinars. You can enter those take your time, work your way through them as you are able. And then we also have direct links to the Illinois Energy Code, the Chicago amendments, and the IECC at those Energy Code resource links. So you can see here, direct access to those links so you don't have to go hunt them down yourself, are available on our resources page at our website. This workshop is part of a series that we are doing for this program year, focusing on energy code compliance and improving compliance throughout the state. We do have a webinar series that is running in parallel with this workshop series. Today we are covering the commercial plan review. Coming up, we have commercial site inspections in May, and then we'll be going over commercial HVAC and having a code panel discussion later on in the year. So when do the energy codes apply? When you're working through a project, it is helpful to know if your project does have to comply with energy code minimum requirements. The 2015 International Building Code in the opening sections has a list of work that is exempt from a building permit, subject to local codes. But in general, this following list applies. In short, if you're doing minor work on a building as far as repairs, moving casework around, such as cabinets, things like that, if the work is generally aesthetic in appearance, then the energy code is not going to be triggered. But you do want to check. This list can be modified by your local building office, so do check with the local building office whether a work permit is required. If you do have to pull a permit, then that triggers the energy code for compliance. So how do you know if you're in a commercial building? Per the 2018 IECC section C202, all buildings that are not included in the definition of a residential building are a commercial building. As we've covered in the past, residential buildings are detached 1 or 2 family dwellings or multiple dwelling unit buildings, 3 stories in height, with an amendment in Chicago to go up to 4 stories, or less above grade, where residents reside on a primarily permanent basis. Commercial buildings are all other structures. In the first sections of the code, section C103, the construction document requirements are listed for the energy code. Construction documents must be provided to a code official, prepared by the design professional, where required by local statutes. Throughout most of Illinois, that is the requirement. The design architect or professional engineer must sign off on those drawings. Information on those construction documents must be drawn to scale, must clearly depict details and provide sufficient detail on building systems and features. And we've included a list here that summarizes the requirements that must be in the plan drawings for energy code compliance. So you have to denote your insulation materials and their R value. That includes the insulation material type and thickness. Fenestration U factor, solar heat gain coefficients. If you're doing an area weighted factor, you have to calculate those and include those in your documentation. Mechanical design criteria, including equipment sizing, load calculations, mechanical and hot water system details, economizer descriptions, control narratives for those systems, fan power and controls, duct and pipe details, including duct sealing, insulation, and location, lighting fixture schedule with wattage and controls, daylighting zone depictions, and air sealing details. These details can be in multiple places in your drawing sets and your specification manuals. What we've been recommending throughout most of this program year is that somewhere you have a centralized summary table of where to find this information for your code official, and that helps speed up your plan review process. It can be a summary page in the plan drawings or a summary table somewhere in the specification manual with just denoting where to find these materials. It also helps to cross-reference these materials through that table to make sure if you change something on the plan drawing, that information gets updated in the specification manual and helps avoid having potentially conflicting information as projects get updated over time. So what do those code compliance summary pages look like? In many jurisdictions, an example here from New York City, The application form has a code summary form to it. We've actually been helping to develop one for residential buildings. Um, this is an example of a commercial compliance checklist. Um, the New York State Energy Office, New York City Energy Code Office has really good examples of how to document energy codes. We've been pulling a lot of examples from there on summary tables for permit forms, compliance checklists, and other items. So it's a good resource to look into. Another thing we'd like to highlight here in the state of Illinois is the Chicago Building Department's permit form. They have energy codes specifically called out on that form with an area to check off which compliance path you are using for your project. And this is really helpful for the code official to know what materials to be looking for in your project. If you're doing a comm check, they're going to be looking for that output report and those summary forms. If you're doing a prescriptive path, maybe they're looking for a tabular entry, either your plan drawings, the spec manual, or as a separate compliance form in your summary information. If you're doing the energy cost budget, they know to be looking for information on both the model for the energy code budget design and your improved design. So this is very helpful information to help the code official understand what to be looking for in their compliance documentation. Before we move on to the envelope, we do have an initial poll. We just want to know if you picked up an energy code summary sheet is required by the 2018 IECC. Is that true or false?
As we are going through here, if you do have questions during our presentation, go ahead and do enter those in the Q&A function that should be found at the bottom of your screen. So just so you're aware, as we're going through, we may answer those questions as a part of the presentation or at the very least at the very end of the presentation. We'll also make sure that we're able to document those for our future reference. Or if we're unable to provide a clear answer today, we can follow up with you following the presentation.
Okay, we're going to end that poll. Looks like we got most of our answers in. Most people said true. The 2018 IEC actually does not require an energy code summary sheet. This is a recommendation we've been making to help speed up the review process. Some building departments may have it as a requirement of their permit form, but the 2018 IECC does not require a summary sheet. It does require documentation in your drawings and manuals, but as far as a specific sheet that documents that, that is not a requirement. All right. So we will turn it over to Ryan to cover plan review for the building envelope.
Well, thank you, Sean. So we're going to be looking at the building envelope here, and do have several critical items that the prints typically do show, including cross-sections of walls and other areas of the structure. And these are very critical for detailing and verifying continuity, because a lot of the challenges that are run into are due to challenges of constructability, and are the walls and roofs and are these assemblies able to be constructed as drawn. And with some of these, it may even be particular construction order can come into play. And so something else that these cross sections can help with is, as you're going through and being able to calculate the assembly R values and U values and U factors, as we're going through here, we can basically draw our a line through this wall assembly, and we can follow it right down our assembly table. So here it's showing 2 inches of rigid insulation for an R10, 8-inch CMU, 1.83. Something to note here is, here we have an R15 insulation bat product that is given an R value of 4.9. We'll touch a little bit in a moment on that. But something to note is this continuous insulation on the outside being 2 inches. If that was upgraded to 3 inches of insulation on the outside, that'd be an R15. So that extra 1 inch of continuous insulation would perform as well as the entire bat insulation and cavity insulation that was placed on the inside of this wall assembly. So that is something that you may look at as part of your design and saying, can I make a trade that might be better performing, as well as if we do improve this insulation on the exterior up to R15, that leaves that cavity available for running electrical and data cables and other things, which would otherwise then have to be insulated around and may increase the difficulty of that insulation. And so again, considering the construction order and constructability, putting continuous insulation on the exterior of a building may be easier, even if it's a little bit more expensive of a product than the bat product. So here, just an extra inch of insulation on the exterior would avoid the entire process of insulating the entire the cavities on the inside. So, and one of the reasons why that R15 bat turns into an R4.9 is shown here. This table that's in the code book demonstrates the effectiveness of R values when using steel stud wall assemblies. And so what this is showing here is somewhere between half and 2/3 of the insulation value that we paid for in our cavities is gone because of thermal bridging through these assemblies because of the steel wall studs. And what this can lead to, if you have substantial thermal bridging, is ghosting. That you can see here on the left is stud cavities where you can see dirt has attached itself to the condensation that builds up due to the thermal bridging in the winter. On the right hand side, this is a precast building, and you can see all the dark squares from the various lifting points and things where you have a structural bridge between the inside and the outside of the panel. So even though these are insulated concrete panels, there is thermal bridging wherever there's anchor points. And so being aware that the ghosting that you see here is not actually what the problem is, but it's actually the symptom of this problem. The problem being the thermal bridging, and the symptom shows up in ghosting from dirt adhering to condensation that forms on these walls. So, as something that the code does call for is schedules for various fenestration. Here is demonstrated as a fenestration table, including the sizing, any projection factors, which these, if you do go through any energy modeling, these come into play. Also, the projection factors do impact what the criteria is for various fenestrations, with fenestration having larger projection factors, being able to provide a little more lax and a little less stringent requirements for these fenestration assemblies. And so we're going through, it even details out make and model, what the U factors are, solar heat gain coefficients, and visible transmittance, as well as air leakage rate. A good practice as you're going through and developing these tables is to go ahead and include the whatever the energy code requirements are for, which makes it for a very quick and easy cross check. In W1, it has an assembly U factor of 0.33, which is at least as good, actually a little bit better than the code required. Solar heat gain coefficient 0.38, that meets the requirement, and 0.16 is better than 0.2 for air leakage. And so again, as plan reviewers, this makes it much nice and easy and quick for them to go through and just double check. Also, when you're doing this, make sure that you do have your code version at the top. This will help as you move from version to version of the code. Fortunately, the state of Illinois adopts the energy code on a statewide basis rather than most building codes, which are adopted on a local basis. Right now we are on the 2018 version. It is anticipated that we are going to move to the 2022 or 2021 version of the International Energy Conservation Code as the basis of the Illinois Energy Conservation Code in the summer of 2022. So permits beginning summer 2022 will likely be falling under the 2021 International Energy Conservation Code. So as we're going through the air barriers, making sure that we do have continuous air barriers and being able to verify the continuity of the air barriers, because air leakage not only loses energy, but commonly will bring moisture and vapor with it through leaks. And so if you do end up with problems in the air barriers, that can lead to substantial issues of moisture, which can lead to mold and mildew. So having a continuous air barrier is very important. And something else that we had shown earlier with some of these detailed assemblies, and we'll show a few more coming up here, is being able to detail wherever dissimilar materials come together or where joints come together, understanding and detailing how that seam needs to be made. Because rarely do products have issues failing in the field of the product. It's normally at the edge of the product or where two things overlap. So also making sure as we're going through for penetrations, anytime the air barrier is penetrated, being sure that that is sealed to reinstate the integrity of the air barrier, whether that's through caulks, gaskets, or other sealants. And if you do have any recessed fixtures that are in that air barrier assembly, more commonly found in residential construction, but there is several commercial buildings that do resemble residential. Being sure that any recessed fixtures are insulation contact rated and listed as an airtight. So again, wanting to that's a potential hole in that air barrier and making sure to reseal that. So as we're going through here, when we're going through and making sure that we're just following along, this is good for review, is to basically take your pen or pencil and outline the barrier here. You can see this one has been outlined with a blue dashed line going through and following all the way from the top of the assembly all the way through the bottom. And so anywhere we do have two things coming together, did we call for an appropriate sealant method and making sure to reinstate that air barrier. And throughout this, not only do we have wall assemblies as you get up to parapet walls, and how are you going to get that air barrier continuous all the way through there. And then here on the right hand side, this appears to be perhaps a common party wall separating two units in a commercial building. And so making sure that we're sealing the exterior, but here they've also called for sealants in the party wall to make sure that we're isolating one side from the other. Again, we don't necessarily want to have air, which commonly along with air will lead to sound transmission. So for this, they probably included some sealants for to aid in sound mitigation between two units as well. So this is something that air barriers can be very useful as you're going through. And beyond the air barriers, next, commonly with the air barrier is going to be your thermal barrier. Those will typically be either the same material or at least in intimate contact with one another, such that air does not pass through your thermal insulation, which can degrade the insulation value of that. And so here on the left, where the window is set out from the wall towards the outside, and so you can see the red arrow here indicating substantial heat passing from the inside through to the outside because the thermal barrier is not lined up between the wall and the fenestration here. So pulling this fenestration in so that it's aligned with that wall can provide a much higher performing wall assembly and dramatically reduce this thermal bridging at the sill locations. And so again, being able to draw straighter lines is generally helpful for design and as well as performance. And something else that we call out here is being aware that there are 4 control layers that we are dealing with in buildings. We have bulk water, which is typically the furthest outside layer. And then we have the air control layer, thermal control layer, and the vapor control layer. So it's not uncommon for materials to serve at least one, if not more than one purpose here. So you may have some insulations are actually can provide that they are an air barrier, thermal barrier, and a vapor barrier, depending on the type of insulation and the thickness. So being aware that there are these 4 different control layers, and as you're going around your drawings with your pen to verify the continuity of your air barrier, it may be good to go around and draw each of the 4 control layers to again make sure not only that they are continuous, but you identify wherever there is a discontinuity or 2 materials come together, and have you made an appropriate joint for those. For slab edges, the code does call out for various insulation requirements. For heated slabs, the insulation requirements are a little bit higher, as well as requiring insulation under the entirety of the heated slab. Again, trying to provide that thermal break between that heated slab and the ground so you don't end up with putting the heat into the slab and then it goes into the ground. We want to make sure that that heat that you put into the slab radiates into the space that you're trying to heat. And something we have come across a fair number of questions on is for buildings that may have traffic at them and being able to protect those slab edges from the traffic. This is one of the reasons why the chamfered insulation detail, which had previously been used, has kind of fallen out of favor, is wherever those edges are, it tends to be a very weak point and break apart. And so similarly, if you have slabs that have traffic, could be loading bay doors or other similar things, the market has now come out with some new products that can help with those slab edges and provide a mitigation to that thermal bridging rather than just bringing that slab all the way across that opening, being able to install some sort of a thermal break for that rather than just having, if you just put your 2-inch insulation in there and had it exposed, it would get damaged, not to mention the surrounding substrate would be damaged as well, likely. So some of these actually even build in insulation to them, so they're not only structural, but they can either have insulation or at the very least a good thermal break. So being aware that those are newer products to the market and may be available. Some of these are even designed such that where you'll have the projecting balcony, the concrete slab balconies projecting out from buildings. These are now, there's now products that can actually support those projections without crushing too. So with that, I believe we've got another poll question here. And I believe so for our poll questions, first looking at how much does metal framing reduce the effectiveness of cavity insulation negligibly, nominally, substantially, or totally? And what is one way to verify the continuity of the air barrier? To look at the prints, follow it with a pen or pencil, rely on the designer's word, or rely on the contractor to get it right.
Did have a question come in on the parapet wall graphics, and it came in when we were switching between. We had one parapet wall that had cavity insulation behind it, so the air barrier kind of backtracked into the wall assembly a bit, and one where there was continuous insulation on the outside of that wall that tied in, so that made up the air barrier, thermal barrier, and vapor barrier. So that's why, depending on the construction of your parapet walls, there can be different details. So it all depends on what you select for that continuous exterior insulation, or if you're doing a cavity insulation type design.
We do have a question here about an assisted living facility, whether that would be qualify as residential or not. And so we'd look to the definition of residential building, which there is an Illinois amendment on this. So this is what the definition is in Illinois. And so here it's noting any building that is 3 stories or less in height above grade that contains multiple dwelling units. So that may or may not be an assisted living facility, depending on if it does contain multiple dwelling units, in which occupants reside on a primarily permanent basis. So they probably would qualify under that part. An assisted living facility is not one of the specific items listed in the definition, such as apartment houses, convents, monasteries, fraternity or sorority houses, dormitories, etc. So again, that would probably depend on the type of assisted living facility and if it has multiple dwelling units, which I believe must include permanent provisions for living, sleeping, which they generally would, but also cooking. So it may depend on whether there's permanent provisions in each of the dwelling units for cooking or not.
Okay, looks like we've got most of our poll answers in, so we'll share those results.
All right, as far as metal framing, it does substantially reduce the effectiveness of cavity insulations. Looks like most people picked up on that. And yes, the continuity, the pen or pencil test. Follow it along that way. So, all right.
Okay, we'll move on to our plan review for mechanical systems. So most drawings now, similar to the architectural summary that has notes on fenestration schedules and insulation requirements, there's also a mechanical compliance summary now, and it's usually built in somewhere we see on a regular basis around the equipment schedules either a preliminary page to those schedules or mixed in with them. Just denoting cooling load calculations completed in accordance with ASHRAE ACA 183 or using a manual N, which is the commercial equivalent of a manual J load calculation or some other approved software. Testing and balancing notes, notes on commissioning, when that's going to occur. Usually those are just kind of bullet point summary details. And then most of the other mechanical summary requirements are contained within the equipment schedules because you're calling out fan horsepower, CFM, equipment capacity, and efficiency requirements. And those all will get referred back to the energy code tables for those minimum efficiency requirements, and so on and so forth. Some things to be aware of. Mechanical system sizing is very important now as we're moving into more and more efficient buildings. Kind of the old rules of thumbs for sizing equipment don't necessarily apply anymore. And so we're relying more and more on software programs to calculate the complex interactions between the envelope, equipment within the building, electrical and lighting loads. And those approved softwares can range anywhere from eQuest or Energy Plus programs to proprietary programs like the Train Tracer program or Carrier HAPS load calculation program. So these are all approved technologies that are in common use for equipment and load sizing. The Energy Code does specify specifically that those programs or any equipment sizing calculation should be based on the ASHRAE ACA standard 183 or an approved technology. Most of those softwares that are available have some kind of basis in their calculations on either the ACA Manual N or the standard 183 for design. As far as documenting those compliance calculations, if you're using a software program, generally it will produce a equipment load calculation report and an equipment sizing report. We've shown an example here from the Carrier HAP program for the load calculations for the different spaces in the building. Usually that's submitted as part of the support documentation. And then when you get to the equipment schedules themselves, that's when you're looking at the total capacity of the equipment, airflow, minimum outside air requirements. And so documentation of code compliance for those mechanical systems has been fairly standard for a long time just because it's integral to the design of those mechanical systems. The really big change now is the greater reliance on load calculations to actually size that equipment. Adding that supporting documentation for the calculation of those loads in the building that results in the proper sizing of the equipment is more important now. But key things to be aware of in this documentation, individual space loads is important. Not only does that impact the sizing of the equipment, but it also impacts sizing of the ductwork and airflows to those spaces, impacts the ventilation requirements for those areas, design total airflow of the air handling system. Minimum outdoor airflow must be documented as well. System capacities and efficiencies of those systems need to be documented, making sure they comply with the minimum requirements in the mechanical tables of the IECC Energy Code. And system pressure drops. The pressure drop is a documented requirement. It helps for sizing of those fan motor systems. So all that information is listed in the section 103, C103, as required mechanical system documentation. Something else to be aware of when looking at mechanical systems is there are 3 duct pressure classes, and the Energy Code does specify in the text 4C403 11.1 that those pressure classes must be called out either in the plans or the specification manuals. But you've got low pressure duct systems where the pressure design is less than 2 inches of water gauge. These are the only commercial ducts that do not have to be sealed along all joints. There are some types of transverse joints, or sorry, longitudinal joints, ones that kind of run long ways down the ductwork, not ones that cut across the ductwork. As long as those are not snap or button lock type seams, Those joints are not required to be sealed. Um, the seam that's usually used on those is usually an S-clamp of some sort, is considered to be tight enough at that lower pressure to not be a significant leakage point. But as you get up to medium pressure duct, which is typically your main trunk lines coming off of an air handler and the branch lines before a VAV box, those are required to be insulated and sealed. And then when you get up to higher pressure ductwork, it's usually the main plenum right after the fan, um, or larger industrial duct systems that have higher pressures and higher flows. Those are actually the only commercial duct systems that are required to have a leak test conducted per the SMACNA leakage test manual. It's the Sheet Metal Manufacturers Association. To have a leakage class of less than 4. There's a specific calculation that's listed in the code section that's based on the pressure in the ductwork and the flow rate through that system that converts the pressure and relative leakage rate of that duct system that gets tested into a leakage class. And so as long as that leakage class is less than 4, that ductwork is in compliance with the energy code. So it's important to be aware of those 3 different systems, classes for duct pressure, and that they do have differing requirements for leakage and pressure testing, leakage testing. Something else to be aware of, duct sealing is a major requirement for duct systems now. While only residential ductwork is required to be pressure tested for all duct systems, and therefore duct sealing has become much more common and much better in that system just because of that requirement. Since commercial duct systems don't have a testing requirement, you're relying a lot more on proper detailing of duct sealing and proper callouts in your plan drawings. And it's something that we don't typically see in plan drawings. We usually see how to connect the joints, how to suspend the ductwork from hangers and things, proper support lengths in the detail drawings. But it's not often that we see in drawings proper sealing, and particularly for flex duct, connecting that flex ductwork to solid ductwork, sealing that up, and then pulling the insulation over that joint. And when that's not properly detailed, we typically see leakage underneath taped up insulation stuff on the ductwork, where air is leaking into the duct insulation, and that can result in condensation and damage to that ductwork insulation. And later on down the road, we've actually seen that leakage come out through that insulation and show up on the ceiling as water spots and leaks, and sometimes gets falsely assumed to be a roof leak. So very important to, when you're looking at your drawings, it might be beneficial to include some documentation on proper duct sealing techniques and strategies to make sure that these systems are properly designed and going to be airtight. Because we really want to make sure that the air we're conditioning is actually getting to the spaces that need it. Very common with a lot of commercial systems to have open return plenums above the ceiling. And if that ductwork isn't properly sealed, leaks from the supply get drawn straight back to the return, and you're not conditioning the space in the building. That can have a big impact on the efficiency of the mechanical system. Another major component as buildings have become more complex over time is the system control narrative and sensor graphics. We're starting to see now, as buildings have become more and more complex over time, that these control drawings are starting to be a separate component of the mechanical drawings. They used to be kind of blended in certain places, but now we're starting to see more and more there's a specific set of control drawings that includes the control narrative along with a graphic of where the sensors should be located and the general kind of strategy for the layout of those systems. So again, we can still at times for simpler systems see these kind of control narratives mixed in with the mechanical drawings. But we are starting to see, especially for larger, more complex buildings, a separate control drawing set. Things to make sure to include in that control narrative for your system: the sequence of operations for the economizer system, damper operations, sequencing of the heating and cooling coils, particularly if you're using a hydronic system, to making sure that you're not doing simultaneous heating and cooling. Fan speed control sequences, how that's related to static pressure controls in the building, how that's related to demand from the actual spaces. There's different control strategies and methods for controlling that air pressure balance. So those are kind of the key things to make sure that are covered in that system. Also, occupied and unoccupied setback controls for the building. How is the building going to transition from an unoccupied setting back to an occupied setting? So those are all very key and important things to make sure that those narratives cover. We do tend to see very good documentation of that. So we do have our next section is plumbing requirements. Again, one of the things we see in the control drawings is call outs for insulation types. We don't necessarily see details on how to properly install that insulation to make sure that it's not compressed, going to become damaged over time, exposed to conditions where it's going to degrade. And so one of the things we like to see called out on plan drawings where you've got tight bends in plumbing and piping or refrigeration piping, that those joints are mitered so that as you wrap that insulation around the pipe, you're not compressing the insulation on the inside bend and reducing the insulation value, and stretching it on the outside, which puts stress on it and can split open the seams if you're using that pressed together foam pipe insulation. And also that's going to thin the insulation on the outside of that bend and reduce its effectiveness there because as it's stretched out, it's also compressed. So using those mitered joints just helps ensure that that insulation maintains its proper thickness and isn't put under stress that's going to degrade it over time. Something else to call out in details is use of either fitted insulation materials for pipe fittings, such as valves, balancing cocks, things like that, or some kind of blanket wrap insulation that provides a little bit more accessibility to those systems. We do find over time those blanket wrap systems tend to degrade, especially as they get leaks, particularly on hot water and steam systems. They tend to dry rot that material and degrade that insulation. These foam fitted covers for insulating those joints tend to be a little bit more durable, although they are a little bit more expensive. But they attach in about the same way, just some straps on the outside that hold the two clamshells together around that fitting. So it may be worthwhile to have a little bit more expense for a more durable insulation to save on the expense of maintaining those and replacing those down the road for the client. Something else to be aware of with our service hot water systems is most all hot water piping needs to be insulated. There is a handful of locations where heated water may not need to be insulated, but there are usually fairly small, such as small valve strainers and unions that are about 1 inch or smaller, that the Energy Code does have exceptions for insulation requirements. Even though minimum insulation is specified in the code, it's often a little more economical to add extra insulation in some locations. You can see in the table here, we've highlighted a row where specific insulation thickness is required. For 3 of these columns, it's 1.5 inches of insulation. For the lower columns, it's only 1 inch of insulation. It may be beneficial to specify 1.5 inch of insulation across all of this. You get a little bit more insulation value on the smaller pipes, but you're more consistent with the insulation type. And so you can probably save on bulk purchasing where you're not using 2 different sizes of insulation. And also increased insulation, especially since the Energy Code for most service water systems is going to require some kind of circulation system in order to maintain a heat source close enough to your fixture that you get ready access to hot water. There's a lot of heat loss that comes from those circulation systems, and a slight increase in that insulation beyond the minimum Energy Code requirements can result in a lot of energy savings for the client down the road, as those circulating systems are essentially just little hot water pipe radiators in the walls of the building. So something to look at, the trade-offs, long-term energy costs versus that upfront insulation cost for the client. Most commercial buildings will require either some form of hot water circulation system or point of use water heaters. And the main reason is these minimum volume or length requirements between the source of hot water and the fixture. As you're seeing here, um, most commercial buildings have about a 1-inch pipe, maybe about 200 feet from the hot water tank out to the lavatory. And that's about 1,000 ounces or nearly 8 gallons of water. Using about a half gallon per minute aerator would make 16 minutes to get hot water from that hot water source to the fixture. And so that's why most of these commercial buildings now have a requirement um, that the hot water source be close enough to the fixture that you've got ready access to hot water. And that usually means you're going to have some kind of circulation system or point of use hot water, um, such as an instantaneous water heater, to provide heat to those fixtures. Um, the reason we call this out is that when you look at the energy code requirements for circulation systems, depending on the type of system you use, they both have a demand component to them. So if you're using a C404.6.1 denotes the control requirements for a circulation system, and C407.7 is for a demand recirculation system. But both of these have a demand component where the pump doesn't start until there's an identification of demand for hot water within the occupancy. For a circulation system, this is usually a flow valve on the cold water inlet to your hot water tank. As hot water gets drawn out for use at a site, cold water starts to flow in. That triggers the circulation pump to activate and push hot water throughout the plumbing system. And then that pump is supposed to turn off once that circulation loop is back at its design temperature, um, usually about 120 degrees. And it's supposed to stay off until there's another call for demand for hot water. For a demand recirculation system, that flow sensor is moved out to a fixture unit or some kind of occupancy sensing device in the lavatory, some system that's directly sensing occupancy use instead of a flow sensor right by the hot water heater. So important to know, most commercial buildings are going to have some kind of requirement for a circulation system. Those circulation systems do have a demand component if they are used in the building. You can avoid having to do that if you put in instantaneous water heaters close to those lavatories. That avoids that demand time for pumping hot water to those fixtures. So important to be aware of. We do have another poll here covering those mechanical sections. So I wanted to launch that polling. Which of the following needs to be documented in the mechanical plans? It is a multiple selection answer, so select everything you think is correct. Do you need to document the duct pressure class, duct sealing locations, mechanical equipment capacities, and a control narrative? And then for the energy code, does that require hot water circulation systems for domestic hot water systems, true or false?
Looks like we did have some more questions come in. Here's a clarifying question about something I believe I mentioned earlier. The question regarding if the 2018 IECC applies statewide, and it is adopted by the state of Illinois for all jurisdictions who issue building permits. That is what triggers the Illinois Energy Conservation Code requirements. And so it is up to the local jurisdictions to enforce or potentially enforceable through the Professional Licensing Act, because one of the ways to demonstrate compliance is to have drawings stamped by a professional engineer or architect.
Okay, looks like most people have answered our polling question. Got a couple more coming in here. Give it another second or two. All right, looks like we got our results in. So the first question, all of these are required in the mechanical plans or the specification documents. They're all requested in the IECC for documentation. So do you have to document the duct pressure class? Usually that's done in the specification manual, although sometimes we do see call outs on the plan drawings. Duct sealing locations does need to be documented. Again, usually proper duct sealing is documented in the specification manual. as far as the attachment of joints. But we do see in some select plan drawings that they are documenting that. Mechanical equipment capacities and control narratives do need to be in there as well. As far as does the energy code require hot water circulation systems? It's not a required as far as a mandatory measure, although the language in the code does essentially force you to either have a hot water circulating system or a point of use source near the fixture. So you do have the option there. You're not required to have a hot water circulation system, although with most building designs, we find that that is the more economical option, and most people choose it. With that, I will turn it over to my colleague Ryan to cover the electrical section.
All right. So for the electrical section, got a few different requirements. Code does again list required documentation. Again, most of these are found towards the front of the code book in C103, and calls out that we do need to have the light fixture schedule, including the wattage, which most documents do, but also need to have that control narrative. So again, similar to the HVAC and mechanicals, making sure that we do have control narratives for the lighting systems. Along with that, the plan drawings do need to have the daylit zones identified, and we'll talk a little bit more about that, but some different options would be perhaps either shaded or hash marked, and it is good practice to also include a plan drawing that does not have them as well. So for reproduction or other needs in the future, they cannot reproduce either the ones with the daylit zones or the ones without, depending on what they need. And so lighting fixture schedules, we do normally see that the wattage is listed. Something else that can be very helpful, but not required by the code, is to go ahead and list the quantities of the fixtures. And so it's real quick and easy for a plan reviewer to go through and just multiply across for each fixture how many they have, what the wattage is, to quickly come up with the total building wattage, which again makes it very quick and easy to check against the lighting budget, depending on your compliance path. Something that we are seeing is with the advances in LEDs, we're not really finding too many times where it's difficult to meet the lighting power budgets, as we're now seeing designs able to be achieved with less than half a watt, sometimes as low as a third of a watt per square foot. So that's something that can be fairly easy to do. And again, as part of this, making sure that we're doing our lighting power density checks. So if you're doing the prescriptive path, going through and just double checking, ComCheck makes this very simple through their lighting power density report. Here you can see where it gives the budget of 134,000 watts and the proposed design 97,000. So since the proposed is less than the budget, this one complies. And so the code does allow you to do either building area method, which is a fairly simple calculation, or you can do a more detailed space by space method. So here we're showing a plan drawing where the daylit zones have been shaded in here. Again, if you're choosing to use shading, it might be good to have a second drawing that does not have it shaded for reproduction into the future. But here you can see they've got, looks like windows around the perimeter, and then the daylit zone flowing into the building from there. And so as far as the control narratives, this may be provided through just a tabular summary, such as shown here, along with some additional descriptions about what each of these a multi-zone switch, what's that going to be? Key switch, how is that going to be controlled, and so on and so forth. And talk a little bit more about commissioning in a bit here. And so providing this tabular summary can be fairly useful for the commissioning process. And so the code calls out several locations where occupant sensor controls are required. So a few of the newer ones are open plan office areas, and in warehouses they clarified this as the storage areas. So even as you go through this list, a lot of these are locations that have unpredictable occupancy, because while offices might be potentially occupied, between hours of 8 and 5, the predictability with is that office going to be fully occupied between those hours is less predictable. And so for areas with transient or unpredictable occupancy, that's where the code does call out that these must have occupant sensor controls. There may be other locations throughout the building that may use occupant sensor controls for ease of controllability and code compliance, but these 11 locations must have them. Code also calls out for if you do have multiple dwelling units, and so you're in an R2 occupancy, that you do have individual dwelling unit electrical metering. This could either be through a system that has monitors several different occupancies through a single front end, or perhaps more commonly meter stacks, as depicted here on the right, where the utility provides all the individual metering. So elevators, this is something that's been brought into the code here recently. And so because this normally is perhaps not driven by the building design, but needs to be called for in the specification documents for the elevator selection, making sure that we do have the controls for elevators, minimum lighting efficacy, that's generally not too difficult to achieve, but also the controls for the fans. And the bigger piece is the controls to deactivate the lights and the fans when the elevator is stopped, unoccupied, and the doors are closed for over 15 minutes. Understanding that when there's no one in an elevator, the elevator is not going to be afraid of the dark. So needing to turn off the lights and fans when there's no one present for the need to illuminate or ventilate the elevator. Escalators also for either reversible or one-way down escalators, there needs to be either reduced speed when they are empty, or a regenerative drive system. Understanding here if I have a nice long escalator on the left-hand side and I have all this weight going down, that can be used to help power the buildings and help offset the energy that would otherwise be needed for the escalators. And so the down escalator can help provide some energy to drive the up escalator and offset that. So as far as something else to check is to make sure that we do have the right zones specified for exterior lighting, because the budget for exterior lighting power changes depending on where you are. Very few projects are carried out in zones 1 or 4. Zone 1 generally tends to be things such as state and national parks, and zone 4 on the other end of the spectrum is major commercial within major metropolitan cities. And so zone 4 would only be found in the state of Illinois within the city of Chicago, and then only in the major commercial districts as designated by the local planning commission. Think about things such as like Michigan Avenue or State Street, Up in Chicago, those probably are going to be a zone 4. Most all lighting power, or most lighting exterior zones, are going to be zones 2 or 3. As you can see from some of the pictures to illustrate, zone 2 is commercial with some residential nearby, and zone 3 is more remote commercial. So just making sure that we have the right zone classifications for our budget. Because as you see, the zone 2, when you have residential nearby, we don't want to have quite so much lighting in those, particularly as that could be disturbing to surrounding residents. So finally, we're going to talk a little bit about software compliance. And so CommCheck does have the ability to leave comments as part of the design. And so, as Sean alluded to earlier with some of these cross-reference tables, using the comments section within CommCheck can be very useful for plan review and can help expedite plan review. And so here we can see in this particular section, there's a comment left saying, it's in the plan documents on page 21, section 3A. So the plan reviewer is checking to see, is this met? They know right where to go. They can find it, check, it's met. Okay, moving on to the next thing. So this can be very helpful. So we do encourage people to use this comment section, as CommCheck does produce these plan review documents and checklists that can be turned in with, submitted with your submittals, and helping to move things along can be very useful. Some other, if you're doing an energy performance compliance path, there's many different programs that can be able to use this through a DOE2 modeling software package, which could go under any number of names, Energy Plus, CAP, Train Trace 700, among just a few of the many options out there. So with building performance, one of the things that makes this much more challenging is a performance path has to do two separate, has to go through and do two verifications and set up two models. The first being a reference model and the second being a proposed model. So the reference model is modeling a reference design that is exactly code compliant, that kind of matches or is similar to the proposed model, but meets just the minimum basic code requirements for each of these. And as you see here, several of these call out as far as things that are the same between the two models, the reference and proposed. Obviously, we want to model a building that is the same size with the same surface area, oriented in a similar fashion. The fenestration areas would match if the simulated, if the proposed has fenestration not exceeding 40%, then those would also match. So again, we're trying to model very similar buildings, but show that the proposed model with its upgrades costs equal to or less than the model, or than the reference, than a base code design would cost. So the table does call out, as far as table 407511 does call out the parameters as far as what these models do, and several of the aspects do have to match between the reference model and proposed. So here's a quick thing to check through and say, things, do they have the same areas? Are they the same, facing a similar direction? Fenestration area, do I have the same internal loads? I can't say that I'm going to use high efficiency computing in my proposed design, and my reference design has standard efficiency computing equipment. That wouldn't be that wouldn't be a fair comparison between the two. And similarly, HVAC scheduling, I can't say that, I'm going to operate my building 9 to 5 and the base building is going to operate, 6 a.m. to 11 p.m. That wouldn't be a similar comparison. So with that, I believe we do have a final poll. All right. So which of these areas does not require occupant sensing controls? Open offices, private offices, corridors, stairwells, storage rooms, or classrooms? And number 2, what makes energy modeling more difficult for compliance checks? Is it difficult to get output reports? The modeled building must be larger than the code-built building. The model needs to model 2 buildings, a reference and a proposed design, or the software is difficult to understand.
We did have a question come in early on about if we could elaborate on the products available to protect exposed insulation at slab edges. Some of the different things that we have seen used, particularly doorway thresholds, overhead doors, access doors to buildings. We've seen the insulation trimmed down in a 2x4 or 2x6, whatever is required to cover that gap. Or some other kind of non-conductive material placed in there on top of the insulation just to provide a little bit of structural support and protection to that insulation. We have seen there's the one particular image we had in there was the Energy Edge. It's a foam insulation product that's wrapped in supporting PVC, and that PVC is a C shape around that insulation, supported on the inside of the slab by some metal supporting racks. And that provides a little bit of structural support to that insulation, so as you can build doorway thresholds and things on top of it without leaving that insulation exposed where it can be torn up, damaged, maybe break those thresholds free. For vehicle bays, loading docks for maybe a refrigerated refrigerated warehouse or something like that. We've often seen details where the insulation is omitted in the areas around loading dock doors in order to provide support for the slab there. We don't recommend that because with those slabs, it's a highly conductive concrete there. And so we have seen some people that they take the insulation across on the interior of the foundation wall or the exterior and use either some sort of elastomeric buffer on top of that to provide some support, such as an expansion joint, or they've used a thermal epoxy in there that provides a little bit of a thermal break. It's just not as conductive as the concrete to try to maintain a thermal break between that interior of the building through the slab and the exterior. If you need more detail on specific products, I would encourage you to email us and we can try to give you some more detail.
All right. Have a question here noting that and someone's calling out is one of the other methods for compliance with the International Energy Conservation Code is through using the ASHRAE 90.1 standard, which is generally whichever one is one previous to the International Energy Conservation Code. So with the 2018 IECC, compliance may be shown using the 2016 ASHRAE 90.1 standard. One of the methods in there is the energy cost budget, which is kind of similar to what we had touched on as part of the IECC, where you're modeling what a minimum code building would cost to operate, and then comparing that to your proposed design. So those energy cost budgets and energy performance methods through either ASHRAE 90.1 or IECC. Those can be used to just compare what's the cost of the new building versus the cost of the old building for energy wise, and allow you a little more flexibility to trade. You may trade better fenestration for reduced mechanicals and things such as that. So yeah, someone did pick up that ASHRAE 90.1 is one method to show compliance. Also had another question along that same lines as far as when also picked up as far as the IECC does show that you need to have the new building saves at least 15% over just a minimum code building, and the reason is under the prescriptive path there is the need for an additional what do they call it? An additional efficiency package, which allows for flexibility and has 8 different items that you can choose from as far as how do you want to go above and beyond minimum performance. Typically we see that done through lighting because that's fairly simple and easy to do. And so that's where that 15% comes in, is to account for that additional efficiency measure that the prescriptive path does not have in it. Looks like we also have another question about lighting housings and why they are not insulated. That is a product standard, and so part of that is just how they manufacture those. They are not designed for insulation. However, that's where the code has kind of come in and said those do need to be insulation contact rated such that you have the ability and capability to insulate around those housings.
We'll go ahead and share our poll results here real quick before we get to some further questions.
All right. Which of these areas do not require occupant sensing? Corridors and stairwells are not part of that listing of 11 areas that require occupant sensing controls. That's not to say that you cannot use occupant sensing controls for corridors and stairwells, but they're not part of the ones required in the code. And modeling being more difficult for compliance is indeed do have to do 2 buildings, so you have to have a reference and a proposed. So looks like did pretty well on those.
Would like to touch on our presentation has been recorded. The recording of the presentation and the webinar slides will be available on our website within a day or 2 after the conclusion of this workshop.
Not sure if there's any other questions that we may have coming in.
All right, seeing no further questions coming in, we would like to thank everyone for joining us today. We hope you have a wonderful afternoon. Thank you.